Hi everybody, welcome to This Week in sept28, the online version. So this week we're going to be introducing the group problem, which will be due on Tuesday, September 29th at midnight, basically at the end of the day. And so by then we expect you to submit, just answer the problem. If it's incorrect or correct, just submit an answer. That's worth 1/3 of your grade. The second third of your grade is the discussion. So we're going to put you into small groups and we expect you to discuss the problem with your group. And then after that, by Thursday, October 1st at midnight, you can submit a second answer and that will be your final answer. And the next third of your mark will be for getting the correct answer to the problem. So basically submit the first answer, discuss the problem with your group, and then submit a final answer. Okay. And this week, we're going to be talking about random variables and probability. But what happened last week? Well, we talked about probability, but the probability of events. So here were some of the muddiest points. And they all have to do with conditional probability, Bayes' rule, and other probability rule type questions. So I'll just go over a few. If you roll a pair of fair die, what is the probability of getting a sum of 1, getting a sum of 5, or getting a sum of 12? Okay, so how can we solve this problem? Well, first of all, we need to know what all the possibilities are for rolling 2 die. So we can list the possibilities, we can list the possibilities here. For die 1, we can have the numbers 1, 2, 3, 4, 5, 6. And for die 2, we can have 1, 2, 3, 4, 5, 6. So the sum will be, if the first die is a 1 and the second die is a 1, that's 2, 3, 4, 5, 6, 7. And then so on. So this possibility is 3, 4, 5, 6, 7, 8, and this is 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, and this is 6, 7, 8, 9, 10, 11, and then this is 7, 8, 9, 10, 11, and finally 12. So these are all the possible sums of 2 dice, okay? And so the probability of getting a sum of 1 is 0 out of 36 because there is no 1 and there's 36 possibilities. There's 36 numbers here, 36 possibilities. Getting a sum of 5, well, let's see, all the 5s are here. These are all the different ways to get a 5, and there are 4 of those. So it's 4 out of 36. And getting a sum of 12, well, there's only one way for that to happen, and that's right here. So that's 1 out of 36. Okay. So the next question is this question out of the Open Intro textbook, and if you haven't already downloaded it, you should do so. And we're suggesting problems from this textbook each week. So here's a problem about burger preferences and what gender you are. So the first question asks, and it shows you this basically this contingency table. And the first question asks, are being female and liking Five Guys burgers mutually exclusive? Well, you can see here that Five Guys burgers, there's 6 females who like Five Guys burgers. So the answer to A is no, because there are 6 females that like Five Guys burgers. If they were mutually exclusive, then those two events would not have anything in common, being female and liking Five Guys burgers. And note that that's different from being independent. For part B, what is the probability that a randomly chosen male likes In-N-Out the best? So we have to look among all males. There's 248 males. So for part B, 248 males, and the number that like In-N-Out burger the best is 162. And note that that's the same as the probability that the burger pref is, I'll just say In-N-Out, given that the gender is male. So that's an example of a conditional probability. Part C, what is the probability that a randomly chosen female likes In-N-Out the best? Well, there's 252 females, and 181 of them like In-N-Out the best. So 181 divided by 252. And it's similarly, it's a conditional probability. Probability burger is In-N-Out, but this time conditioned on gender is equal to female. For part D, what is the probability that a man and woman who are dating both like In-N-Out the best? Note any assumptions you make and evaluate whether you think this assumption is reasonable. Well, what we can do is multiply the two probabilities from parts B and C. So that would be 162 out of 248 times 181 divided by 252. And the assumption here would be that dating choice is independent of hamburger preference. So must assume that dating choice is independent of hamburger pref. And finally, for the last one, part E, what is the probability that a randomly chosen person likes umami best, or that person is female? So for umami burgers, there are 6 people who like umami burgers. So that's 6 out of 500, because it's a randomly chosen person, and there's 6 in total, plus a randomly chosen female. Probability of a randomly chosen female is 252 out of 500, because there's 252 females. 252 females. But we have to subtract off the probability of being female and liking umami burgers, which is, in this case, is there's 1 female who likes umami burgers. So that's the 1 here. Minus 1 out of 500. And that's the answer to part E. The next question that I wanted to go over is about drawing box plots. But it's actually a tree diagram problem, or we can use Bayes' rule to solve it. So after an introductory statistics course, 80% of students can successfully construct box plots. Of those who can construct box plots, 86% passed, while only 65% of those students who could not construct box plots passed. Construct a tree diagram of this scenario. Well, what comes first? Well, the first event is, can you construct a box plot or not? And so the first part of our tree, like this, will be construct box plot. And that will be yes or no. 0.8, 0.2. And then among those who can construct a box plot, some will pass the course, yes, and some will not pass the course. And among those who can construct a box plot, Some will pass the course, and some will not pass the course. So in this case, the probabilities are given. This is 0.86. This is 0.14 then, because 0.86 and 0.14 have to add up to 1. This was given as 0.65. So those who can construct a box plot, the probability that they'll pass is 0.65, and then 1 minus that gives us 0.35. Multiplying this probability with this probability gives us the probability of constructing a box plot and passing the course. So we can do that. 0.8 times 0.86 is equal to 0.688, and 0.8 times 0.14 is equal to 0.112, and 0.2 times 0.65 is equal to 0.13, and 0.2 times 0.35 is equal to 0.07. So that's our tree diagram. Now for part B, it says calculate the probability that a student is able to construct a box plot if it is known that he passed. Well, that's the probability of constructing a box plot, but that's equal to yes, given that that a pass is equal to yes. And so we can just get the probabilities off of our tree diagram. So that's going to be equal to, well, the probability of constructing box plot is equal to yes, and pass equals yes, divided by the probability that pass is equal to yes. So for the numerator, that's just going to be this probability over here, 0.688, 0.688, divided by, you can pass the course if you can draw a box plot or if you can't draw a box plot. So that's going to be 0.688 plus this other probability, 0.13, because this is the probability that you can construct a box plot but you still pass the course. So that's 0.13, and that's the answers to that problem. So I hope you've had a good week in Stats 220 online, and we'll see you next week.